All right, I'm going to go through how to fill out the experiment 12 report sheet. That is the acid-base titration using KHP to standardize your NaOH and calculating the percent KHP in the unknown. All right, so when you go to the report sheet, first thing it asks for is the volume of HCl. So number one is the volume of HCl. Simply you show your final minus initial to get your volume of HCl in milliliters. Number two, your volume of NaOH on your data sheet. You have your final initial volumes of NaOH. You subtract those, then you have your volume of NaOH. All right, then to get the RAB, all right, so the RAB just means ratio of acid to base. That is equal to the molarity of your HCl divided by the molarity of NaOH, which is equal to the volume of NaOH over the volume of HCl. All right, this comes from the titration that we did with the strong acid, strong base, where you had HCl plus NaOH yields H2O and NaCl. Everything's 1-to-1, so you did a MV over C is equal to MV over C for your acid and for your base. All right, so that's your molarity of your acid, volume of acid, coefficient. So the coefficients were put in. They were 1, and if you solve this for your molarity of your HCl and then divide by the molarity of your NaOH, that will give you your volume of NaOH, and then you'd have to divide by the volume of HCl. So it's just coming from the acid-base titration. But we have two unknowns. We cannot solve it. But what we can do is get the volume of NaOH divided by the volume of HCl. So you look at 1 and 2, and you divide your volume of NaOH divided by your volume of HCl. So for the example that I have, when I got the volume of HCl for run 1, it was 22.81 milliliters, and the NaOH was a 12.80 milliliters, so whatever you got for year 2. So then you just take your volume of your NaOH, which is 12.80, divided by your volume of HCl, which was 22.81, and that gives you a 0.5612. All right, so you put in your data, you divide it, you're just taking your volume of NaOH divided by your volume of HCl. All right, then in number 4, you just take the average. So you add RAB run 1 plus RAB run 2. You know how to take a average. RAB run 3 divided by 3. All right, and so then you've got to take your standard deviation. So, all right, so I'll put in the numbers. So the first one was 0.5612. The next one on this data sheet that I have picked out was 0.5600, and the next one was 0.5616. So after you get your three numbers, you add up and get your average. Add them up, divide by 3, and this is a 0.5609 for the average. All right, so then you have to do your standard deviation. All right, so the equation for standard deviation is in the back of the lab manual. All right, so you're going to take, so this is a long show your work. All right, so you take your 0.5612 minus your 0.5609. So run 1 minus the average squared plus run 2, 0.5600 minus the average, 0.5609 squared plus run 3, 0.5616 minus 0.5609 squared, all divided by the number of runs, which was 3, minus 1. All right, so when you plug that into your calculator, if this was your data, this one gave me a 0.0008. Always give your standard deviation to 1 sig fig. So you don't have to worry about sig figs. You always give it to 1. You do have to worry about sig figs above. So you should have 2 decimal places for all your volumes. And in this case, there was 4 sig figs divided by 4 sig figs. And so the RAB was given to 4 sig figs. Always have to be mindful of sig figs. But standard deviation, you don't have to be that mindful. You just know every time you do a standard deviation, you give it to 1 significant figure. All right, so then to write your average using the standard deviation, this one doesn't change because the 1 sig fig was in the 4th decimal. So you give it to 4 decimals, which was all the decimals, 5, 6, 0, 9. That was the average. And that's plus or minus a 0.0008. So the standard deviation said go to the 4th decimal. So you go to the 4th decimal. So we didn't have to round this one. All right, and so then 7, mass of KHP. You get that right off your data sheet. That's also number 7 on your data sheet. All right, so for this case, I had a 0.3089, and then the second one was a 0.3013, and then the third one was a 0.3086. Again, that just comes right off of your data sheet. All right, so then number 8 is volume of your NaOH. So that is simply final minus initial again, and for the data that I have, it's 14.58 milliliters for the first one and 14.20 milliliters for the second one and 14.65 milliliters for the third one. All right, and now I need number 9. Okay, so this number 9 is where we calculate the molarity of our NaOH. All right, so number 9. So to calculate molarity, you do that from your titration. All right, so the titration equation is MV over C is equal to MV over C. All right, but that's only if you have 2 liquids. In this titration, we had our acid as a solid. So if you have a solid, all right, so molarity is moles per liter times liters. That gives you moles. All right, so that's how you would do it for a liquid. All right, so you have a molarity, mole per liter times liter, that gives you moles. For a solid, you can't do that. So a solid, you have a mass and divide by a molar mass. So you take the mass and divide by the molar mass. So that's grams divided by grams per mole to give you moles. All right, and so when we do our acid as a solid and our base as a liquid, so the acid is the mass of your KHP, because the KHP is the acid, divided by the molar mass of your KHP over the coefficient of your KHP, and that's equal to the molarity of your NaOH, volume of your NaOH, divided by your coefficient of the NaOH. And so your KHP has 1 H, so it's monoprotic, so it reacts with 1 OH minus. And that will give you your water and your KP minus. All right, if you did the net ionic, all potassiums are soluble, so you could get rid of the potassium and that's minus, and you get rid of the potassium and that's then -2. All right, the key is we need the coefficients, and the coefficients are both 1. All right, there's 1 H in that acid. It's a monoprotic acid with your NaOH. So then we just plug in our numbers. The mass of KHP, so that is your data number 7. You just write that mass down. For this data sheet, it was 0.3089. Molar mass is given in the directions for KHP. All right, it is 204.23 grams per mole. KHP is potassium hydrogen phthalate. Phthalate is an organic compound. 1 is our coefficient. Molarity of the NaOH, that is what we are solving for. All right, but the molarity, as I did show up here, molarity is moles per liter. Here is where you get a lot of errors. Now, this volume is not going to be in milliliters. This volume is in liters. And so I have my 14.58 milliliters. All right, so my volume is 14.58 milliliters that I wrote in number 8, the volume of my NaOH, but I have to have it in liters. And so you have to convert your volume into liters. And so that is equal to a 0.01458 liters. And the coefficient for your base is also 1. All right, so when you take your 0.3089 divided by your 204.23, then to get molarity of NaOH by itself, we have to divide both sides by the 0.01458. You get your molarity of your NaOH. When you do this, you get moles, and that is then liters. That's why it had to be in liters, to give you moles per liter. And this one is 0.1037. So that is the molarity for run 1. And so for run 2, you put in your mass that you got for run 2, you put in your volume that you have for run 2, make sure it's in liters, and then hopefully you get a similar number. They shouldn't be that far off. We use the same KHP and the same base each time. All right, so the one I'm looking at, my next one was 0.1039. So this was the first one. The second one I did, molarity NaOH run 2 was 0.1039. They don't have to be quite that close. And then molarity of NaOH for run 3 was a 0.1031. All right, not really expecting them to be that close. This is very, very precise. It doesn't say anything about the accuracy, but it does say something about the precision. All right, and so to get your standard deviation, all right, the average, so then you add those up and divide by 3, and that will give you your average, and if you do that, it's 0.1036. So molarity of NaOH for this example that I picked out, so your average is 0.1036. And now you're going to do the standard deviation again. All right, so you got the square root. All right, run 1, 0.1037 minus the average, 0.1036 squared. Plus run 2, 0.1039 minus the average, 0.1036 squared, plus run 3, 0.1031 minus the average, 0.1036 squared, divided by the number of times we did it, which was 3 times, minus 1. And when you push the buttons on your calculator, you get to 1 sig fig, 0.0004. Again, this is a very precise lab that I had picked out. All right, so I'm not really expecting you to be quite that precise, but if you are, then okay, then it says that your standard deviation says to report to the 4th decimal, and so you would write your 0.1036 plus or minus 0.0004. So you write your average, and you have to round it to the 4th decimal. Well, our sig fig rules already put it there, and so we didn't have to change anything. Make sure you're being aware of your sig figs. Again, standard deviation is always 1. So up here, the reason why I'm giving the molarity to 4 sig figs is because my mass has 4 sig figs, my molar mass has 5 sig figs, my volume has 4 sig figs, and so I give my answer to 4. If the only thing that could be different on yours is if your volume was less than 10, you would have 3 sig figs and you would report to 3 sig figs. All right. So that's our molarity of our NaOH. And now we're going to do our unknown KHP. Make sure you have your unknown number. So this one on your data sheet, it's on your data sheet, unknown number. This one's 32. Make sure you have your unknown number. All right. And so the first thing is massive unknown right off of your data sheet. So it's number 13 on the report sheet. It is number 10 on your data sheet. 0.8701 was the first one. On the one I picked, 0.8701, 0.8701. All right, and the second time, this person used 0.8502, and the third time, this person used 0.8743 grams. All right, so that's your unknown. Mass, so 14, volume of NaOH. All right, so that's just simply final minus initial from your data sheet. This person, it required 10.60 milliliters, 10.59 milliliters, and 10.61 milliliters. All right, so now we're ready to do the calculation. Mass of pure KHP. So your unknown is not the mass of KHP because the unknown has something else in it. So we do the titration, the exact same titration that we did before, except it's unknown KHP, which means it has like probably NaCl, which isn't going to do anything. It's not acidic or basic in your acid-base titration. All right, and so again, we have the mass of KHP. We have the divided by the molar mass of KHP. Again, when it is a solid, it's mass divided by molar mass, the C of your KHP. And that's equal to the molarity of your NaOH times the volume of your NaOH divided by the coefficient of your NaOH. All right, so last time we had pure KHP, so we could put that in there. And that's how we found our molarity of NaOH. So now that we know the molarity of the NaOH, we can use that to find the mass of pure KHP in our unknown. And so your mass of KHP, that is what you are solving for. You're going to divide that by the 204.23 grams per mole given in the lab write-up, the molar mass of KHP. We see that the KHP is a monoprotic acid and the coefficient is 1. Use your average molarity of NaOH, and that was, for this one, 0.1036 moles per liter. And so now the volume of NaOH, we have to convert our 10.6 milliliters, 10.60 milliliters to liters so that it cancels and gives you moles. And so you have a 0.01060 liters and divided by the coefficient of your NaOH, which is 1. All right, so this is the mass of KHP divided by the 204.23. So we have to multiply both sides by the 204.23. And you get your mass of pure KHP in that unknown sample as a 0.2243. All right, in this case, everything had 4 sig figs except for the molar mass had 5, and so I give my answer to 4 sig figs. All right, so now, and then I do that 3 times. So the second time I did it, everything's the same except for the volume. So in this case, the volume was pretty close to the same every time as well. So for the second one, run 2, The mass was a 0.2241, almost exactly the same, because the volume was almost exactly the same. And then for mass 3, again, 0.2245. Again, because the volume was almost exactly the same, we got the almost exact same mass every time. Again, very precise. Precision doesn't say anything about accuracy. All right, now to get our percent KHP, which is number 16, you have to take the pure KHP, and that's what we have right here, divided by your unknown KHP. All right, so the mass of pure divided by the mass of unknown in grams times 100, and that will give us our mass percent of KHP in our unknown. And so we have 0.2243 grams after we calculated it using the titration equation. And in run 1, the amount of unknown used was 0.8701. So times 100. I have 4 sig figs divided by 4 sig figs. 100, when you're multiplying by 100, that is a perfect number. 4 sig figs is the number that is the lowest, so 25.78%. And then you got to do that for all 3 of them. So the next one was 0.2241. And the unknown weighed out for the second one was 0.8502 times 100. And so that was a 26.35. And then finally, the last one was your 0.2245 divided by the unknown used for run 3, which is 0.8743 times 100. And that gives you a 25.68%. All right, so to get an average, you add them up, divide by 3. So number 17 says, what is your average? Add them up, divide by 3. In this case, it would be 25.94. All right, so that is your unknown percent average. All right, unknown KHP, your average. All right, then standard deviation. For the third time, standard deviation. All right, so you've got to take the square root. Run 1 gave us a 25.78% minus the average of 25.94. Squared plus run 2 gave us 26.35 minus the average 25.94. Squared plus run 3 gave us 25.68 minus the average 25.94. Squared, all divided by the number of times we did it. We did it 3 times minus 1. All right, so you push the buttons, you get your standard deviation. It is 0.4. Always 1 sig fig. That is 1 sig fig. So now you got to write your average, which is a 25.94. All right, but you can only give it to 1 decimal. Standard deviation tells you how many decimals you should report your average to. All right, and so that says that you have a 25.9 plus or minus 4%. So this is your number 19. I realize that many of you may not have a number 20, but there is a number 20. So if you have a number 20 is calculate. I'm not going to grade if you don't have 20. I'm not going to count it wrong. Calculate the molarity of your HCl. All right, to calculate the molarity of your HCl, we have our average RAB value. And the average RAB value, which is the molarity of HCl divided by the molarity of the NaOH. All right, or you could go back to the initial titration, which is probably the best way to do it. Yeah, probably the best way to do it. You could do it by RAB. Fine, we'll do it this way, and then I'll show it the other way too. All right, and so now we have our average NaOH. The average NaOH was 0.1036. And we have our average RAB value, which was 0.5609. So we multiply our molarity of NaOH on both sides to get rid of it to give us our molarity of HCl, and that is a 0.05811. All right, so you will need the molarity of your HCl. So at some point you will have to calculate that. But you could have done MV over C is equal to MV over C, and done it that way. But then you would have to take it and do it 3 times and get your average. So the best way to do it is take your RAB value, average RAB value, 0.5609 in this case, times your average molarity of NaOH, and that will give you your average molarity of HCl, which in this case is 8.05811 molar. All right, so that's how you do experiment 12 report sheet.